So in section 3.6, we'll be looking at solving polynomial and rational inequalities. Now we won't be actually graphing, but we will use our knowledge of the graphs of these two functions to help us. Because the idea, skipping past the steps for a moment, when working with this inequality, you won't solve this algebraically, right? Anything an x squared or higher in here, there's no algebra to just move things around and find the answer. Instead, we're going to think about it effectively as a graph without graphing it, because this function here, this is a function. We could think of it like a function, a polynomial function. And asking where this function is above or below 0 is really nothing more than saying, well, this will give me the y value of the function. And if I ask for the y value of a function to be above 0, that's just like asking where will the graph be above the x-axis. Or in this case, below less than 0 is like below the x-axis. And if the or equal to line is thrown in there, that's like saying on the x-axis. So this inequality, we will effectively use our rules for graphing to determine where is this graph above, below, or on the x-axis. And that's going to be our approach. So working through these steps here, the first step is important. If you don't have an inequality with 0 on one side, that's the first thing you want. You want a function compared to 0, which we have. So step 2, factoring. To factor this thing, first thing I'd say is we don't like a negative sign out front. So let's get this so it's got a x squared with a positive coefficient there, and that'll make that a 3x and a minus 40. And notice I'm not going to even worry about this inequality. I ignore it for the rest of the problem until I get to effectively my final answer. I just work with this. So the negative's factored out, and then this thing does happen to factor, so that's convenient. We just need numbers to multiply to negative 40, add to positive 3, so that would be a positive 8 and a negative 5. And that's basically step 2. Step 2 is just factoring. Now step 3 says plot the zeros on a number line. So after having factored, I'm going to go through the next step and point out that this x plus 8 equals 0 gives me a 0 of negative 8, and x minus 5 equals 0 gives me a 0 of 5. So now, these two numbers are the only numbers of importance to us, because if these are the only zeros of this polynomial, these are the only x values where this graph, again, if we were graphing it, could potentially change sign, right? That's the only places that a polynomial function went from above to below the x-axis, or below to above, was at the intercepts, at the zeros. So we're saying there's our number line, but I don't need to label all of it. I just need to think about the fact that there are two important points on that number line, negative 8 and positive 5. Now, something up here that I think is just useful, talking about what happens at those values. Well, what really concerns us is what we're looking for. We're trying to figure out where the function is less than or equal to 0. So if you have an or equal to, that's allowing the points where the graph would have been on the x-axis to be part of your answer. So that's why here on 3b it mentions, if you're answering either of these inequalities with the or equal to, we're going to go ahead and put a filled in circle anywhere that we know there would have been a point on the x-axis. Oops, sorry. Filled in circles at negative 8 and positive 5, because again, we're working with this inequality. Now, from there, the thing we want to know is, where is our function? Is it above? Is it below? Well, step 4, first thing it mentions, just use end behavior. And then we'll talk about the other stuff too. But use end behavior to think about what this function should look like. We know enough about end behavior for polynomial functions. If this is an x squared polynomial, that's an even polynomial. Now, it's an even polynomial with a negative coefficient, right? So the end behavior here, coming from something we've discussed before, the end behavior, because of that leading term being negative x squared, the fact that that's even makes us think about our squaring function, right, the parabola. But the fact that that lead term, or lead coefficient rather, is negative, these two details tell us that we should be thinking about end behavior like an upside down parabola, meaning down to the left, down to the right, or false to the left, false to the right. So on my number line down here, I'm just going to put a couple little arrows signifying that that would have been the end behavior. It is the end behavior for this polynomial, guaranteed. But what's that mean? If it's falling to the left, it's definitely below the x-axis over here, and it's below the x-axis at least until it gets to here, until it gets to a point where it might change its sign, right? So what we know about this entire interval over here, and there's lots of ways you can kind of write this, but I'm going to put a bunch of negative signs just to kind of point out it is negative. It is below the x-axis over there. Now it gets to this point, which came from this 0, which came from this factor, and this factor has a multiplicity of 1, right? There's only one of it. That means with an odd multiplicity, we know it's going to cross, right? Our graph will be crossing at that point, which means as soon as you get to the other side of -8, it's now above. It's kind of doing that hill part of the graph. We know. We don't need to draw it, but that's what it's doing. And so we can expect that it's going to be positive, above the x-axis, for all those points between -8 and +5. It gets to +5, which again was a 0 from a factor of multiplicity 1, so it will be crossing there as well, which aligns with the end behavior of going down, which tells us it's now again below the x-axis for all those points. So you can even, if you want to, you can kind of, think of the sketch of the graph on this number line. I'm just saying you don't need to, but we know that's what's happening. That's the behavior, the general sketch of our function, our original function here compared to 0. And so if that's our function, and we're asking for, where will this function be less than or equal to 0? Less than. Well, less than is below. So that's all of this and all of this. Right? So we want this entire interval here and this interval here. We basically want all of that and all of that. So we just take that and put it into interval notation. To be everything left of -8 would be to say from -infinity, right, just going left forever on the x-axis till you get to -8. Now, -8 has a circle, right, has a filled in circle, meaning we want -8 in our answer, so we use a bracket. And then we can union that, because we're going to hop over all this, to start at 5, which we also, with that closed circle, want to fill in, or want to include. So bracket, off to +infinity. And there would be our interval of x, right? That's what we're really doing. We're finding the x values that would make this true. Any x value in either of those intervals, right, anything less than 8 or larger than 5, if you plugged it in here, would give you a number less than or equal to 0. That's what we just found.